Tech Tip 3. Selecting the proper helix and rake angles for your application. The helix and rake angles on carbide end mills affect the cutting forces, chip evacuation, tool deflection, and overall performance. Selecting the appropriate angles for your application and material can help with optimizing the milling process, improved surface finishes, extend tool life. Helix angle. The helix angle is the angle between the cutting edge and the axis of the tool. It influences the cutting forces, chip evacuation, and tool deflection. Low helix angles, 30 degree to 35 degree. These angles generate less axial force on the spindle and work holding, resulting in reduced tool deflection. However, they produce a more aggressive cutting action, which can lead to chatter and poor surface finishes, especially in long-reach applications. High helix angles, 40 degree to 50 degree. These angles generate greater axial force on the spindle and work holding, which can lead to increased tool deflection. However, they provide better chip evacuation and smoother cutting action, resulting in improved surface finishes and reduced chatter, especially in materials like aluminum and non-ferrous alloys. Rake angle. The rake angle is the angle between the cutting edge of the tool and a perpendicular line to the workpiece. It affects cutting forces, chip formation, and tool life. Positive rake angles. These angles reduce the cutting forces on the spindle and work holding, making it easier to shear the material. This leads to reduced power consumption, lower heat generation, and improved tool life. Positive rake angles are suitable for materials like aluminum, brass, and plastics. Negative rake angles. These angles increase the cutting forces on the spindle and work holding, providing a stronger cutting edge and improved edge retention. However, they require more power to cut and can generate more heat. Negative rake angles are typically used for hard materials like cast iron, hardened steels, and stainless steel. Here's some things to remember when working with carbide end mills. Evaluation. Assessing the end mill's performance and suitability for a specific application. Needs. Understanding the specific requirements of the material and application to select the right end mill. Diameter. The width of the cutting edge of the end mill, which impacts the material removal rate and tool stability. Material. Considering the compatibility of the end mill with the workpiece material, such as hardness and machinability. Inserts. In some end mills, replaceable cutting edges that can improve tool life and performance. Lifetime. The overall service life of the end mill, which is influenced by factors like tool material, coatings, and maintenance. Lubrication. Ensuring proper cooling and lubrication to minimize heat buildup and extend tool life during machining.